Good morning, everyone, and welcome to our big data lecture. In the last lecture, we discussed uncertainty in learning. We specifically looked into conformal prediction and model calibration. And the advantage is, especially with conformal prediction, it's just something you can plug in any of your classifiers, regressors, or almost all of them. And like this, you get a measure of uncertainty. There are other approaches like Gaussian processes, model calibration we've seen as well, which has its pros, but also its cons. And then we looked into big data for NLP. And we started with how we can represent text in a form so that our machine learning models can use them. We saw different approaches, like we could just map each unique word or each word to a unique number. We don't want to be doing that. We've seen why. One-hot encoding works fine, but leads to very large spaces. So we will run into the curse of dimensionality. And word embeddings are something that have become extremely popular in the last few years because we have a low dimension, and that low dimension is densely filled with or a very dense representation of our vocabulary. So typically we just have a few hundred dimensions, while with one-hot encoding, you could run into millions of dimensions, which is sparse, which we don't want. And we've seen how we can learn embeddings. We typically use neural networks to learn them from scratch. But then when you have a pre-trained model, you would just use these vector representations and use them for your own data set. And we've seen that words that are quite similar to each other also appear quite similar to each other in this embedding space, not because we defined which words are similar, but purely because these words appear together or in the same context, and all of that is learned by the neural network. Then we started to look into transformers, and we discussed the generative pre-trained transformer 3. And we discussed it, even for now we have ChatGPT, because in the user interface, you have much more options, so you can manipulate them. And today, we will finish this chapter and talk about ChatGPT. If you want to use pre-trained models, always use Hugging Face or other vendors. It's a very cool portal. They offer lots of pre-trained models. You can also share your own ones if you wish, and always use pre-trained models wherever possible, because you don't want to train these models from scratch, because you will run simply out of money, because you need lots of electricity. Now, today we will talk a little bit about ChatGPT. And first of all, I want to know from you how you are using ChatGPT for which kind of tasks. And we can ask students here in the classroom. For the ones online, maybe send this to the chat. If you have any comments on how you use ChatGPT, and who of you wants to tell me or us what you're using ChatGPT for?
Formal emails.
Writing formal emails, okay. Yes.
How can I solve it? That's how it is.
Okay. We also got other comment, write code. I think for coding, it's extremely helpful, but not just for coding, but also for generating comments, because most coders don't like to write comments, so you can maybe generate them, as well as maybe a good commit message when you commit in Git or some other versioning tool. Formal emails, what I start noticing since ChatGPT has become available, emails sent by students are becoming longer and longer. And then, I don't know, you have like 3 bullet points and you put this in ChatGPT, and I get a super long email and I put it in ChatGPT and ask ChatGPT to summarize this in 3 bullets. That's not the kind of communication we should have. So still send short emails with clear messages. Yes?
Yeah, they have short, but I mean, my English is not good enough for me, so I use ChatGPT to fix my English.
That's great. So I think also if you're learning other languages, such tools can be super helpful. I'll tell you a little bit more today about what I like about ChatGPT and how I use them. Obviously, we can use them to generate code, but I think ChatGPT and other large language models, they're really good in also convincing you of total nonsense, because they can write this and it looks so good. Like here, I asked it how to train a transformer, and I got something like this. But that library or that submodule in Keras does not exist, so it doesn't work that way. So if you put this in your IPython or some other environment, you will notice that you don't have the library. Then you want to install it with pip, and it still doesn't exist. So it doesn't work that way. It's also been argued that much more cybersecurity issues are now coming into code if you purely aim to generate a code. So always take the results of ChatGPT with a grain of salt. You can take it from there and improve it, but you need human intelligence first and then the artificial intelligence. Yet, I think it's a huge opportunity. Most of you here are studying AI. You should be using these tools for coding, because if you don't, you will be put out of business because your competitors, they are using this. And right now, I don't know, they're maybe 20 or 30% more productive. In the future, maybe 10 times more productive. I don't know. We will see how all of this evolves. So use these tools and make sure you're productive and competitive. And I use them also for various emails or to summarize stuff. I also use them when I write papers. So I'm honest about this. When I write a publication, I put in the beginning a footnote and I say I'm using these tools. Obviously, I'm not using directly what they generated, but maybe I have some notes or something and I need some structure or some way to put it in a nice way. And for this, such tools can be very helpful, but obviously I, as the author, I'm ultimately responsible. But these tools simply, they can help me maybe to improve the structure, to get some more input that I wouldn't be thinking about. And then I write this as a comment in my publication in the very beginning, and that's fine to me. Just like 2 or 3 months ago, I wrote a journal paper that explains in detail the foundations of generative AI models. And this paper is also uploaded in our Nextcloud. And it's your task for next week to read it, because I just wrote this paper, so there's no point in turning this into slides, because the paper discusses what is important. Initially, I discussed some early generative approaches like rule-based systems, statistical methods, and so forth. And because generative AI has been there for decades, it's not a new term. Then I write about the emergence of deep learning. Most of you are in our AI bachelor's program, so you may have a background in deep learning already. Feel free to skip that section if you're new to this or you want to get a revision of deep learning. Take a look at it. It explains various deep learning approaches. And from there, I discuss the large language models. I first discuss sequence-to-sequence models, then self-supervised learning, the attention mechanism. We've talked about the attention mechanism briefly in the last lecture. We looked at a first transformer that was proposed 6.5 years ago. I explained the concept of a transformer in here. And then I discuss various foundation models like GPT-3, GPT-4, and so forth. Plus, right now, there are all these discussions around regulating AI and all these fears. I also address this in my journal paper. So these are like 10 or 11 pages. So maybe just read this until next week. And we won't be discussing all these low-level details then in the lecture, because the paper has just appeared a few months ago and is still up to date. Now I said, plus another thing is, I also said a few weeks ago when this course started that I'm super happy that this new Bishop book has appeared during Christmas time or just before Christmas, the deep learning book from Chris Bishop, and this time his son is a co-author, which is the same style as this famous Bishop machine learning book from like 2006, 2007. And this book also just appeared before Christmas, so it's quite up to date. And it also provides an explanation of how these decoder transformer networks work, or encoder, decoder, or decoder, encoder architectures. And there's also a couple of pages on how on large language models. Feel free to read this as a second reference, or just stick with my journal paper, which should adequately cover all of this. Now, I said I'm using this to write papers. Now you're wondering if you're allowed to use this to write your thesis. And what I want to say is, if you talk, or when I talk to my colleagues, that's a very controversial topic, how far we are allowing the use of AI here. I personally think it would not be credible if we teach AI but wouldn't allow you to use it. So what I said is, and I notice a lot of my colleagues, they're trying to ban you from using ChatGPT and other tools for writing your thesis or your code. And they try to find out whether you have used it, and they try to penalize you. So I have changed the game like more than a year ago. And I said, if you're writing your thesis with me, you're not just allowed to use these tools, but I'm actually expecting you to use these tools, because like this, you will be more productive. My approach has led to lots of discussions here in my department when I presented my approach, but we as professors, we're very free in how we supervise thesis. And since that part is not regulated by the state government, we can just come up with our detailed rules of how we supervise thesis. So here in my department, this led to lots of trouble, but others liked my approach. And I posted last year on LinkedIn about this. And then Frankfurter Allgemeine Zeitung, which is supposed to be or known to be the highest quality newspaper in the country, they liked my approach. So they asked me to contribute a guest article in which I describe my approach. The article is in German, but my set of rules is in English, because I just copy and pasted it, or we just copy pasted it into the article. So what I say is, if you do your thesis with me, and this not just applies to thesis, but also to other projects, you're supposed to be using these tools, because like this, you're more productive. But obviously, critically assess the output of those tools, because these outputs may sound very convincing, but they could be totally wrong. Obviously, you need to add references to support certain claims. Check your thesis for plagiarism. From my definition of plagiarism, if you copy-paste from ChatGPT, from my perspective, this is not plagiarism, because it's something new and it's not a citable source. However, ChatGPT may, in some instances, just repeat a sentence that has appeared somewhere else. And that would be plagiarism then. So double check still your thesis for plagiarism. Many of you are doing your thesis in industry. Pay attention if you're allowed to use this if your employer allows you to use such tools, because if you put trade secrets or other confidential information in publicly available large language models, this could lead to dramatic consequences for your future. So check this with your employer, check the privacy policy of tools like ChatGPT and others. If there are certain concerns of your employer, maybe just set up your own language model, use something from Hugging Face and run it on a server or something, or in a cloud provided by your employer, and then you have more control over what's happening. What I also want from my students who do a thesis with me, I want you to describe in an extra section of which tools you have used and how you have used them for what. And like this, I get a little bit of an idea how you have used generative AI tools. And what I keep noticing now for the last 1.5 years is the thesis submitted by students, they are getting better. Students seem to have more time for research and experiments, because some of the writing, some of the coding is getting automated. Not all, obviously, but some. So the theses are going up in quality, but also in content, which is something I find very positive. and the thesis have less typos and spelling errors than before. So, but for that, you don't need the AI to improve. So overall, I'm very happy. And with this set of rules I came up with a year and a half ago, so far, I have not amended it. I just keep using it. I was wondering how stable this set of rules would be and when I would need to amend it, but so far it's going well. So these are the rules if you ever want to do a thesis with me. If you talk to my colleagues, they may have different rules. So now we have finished the big data for NLP, because as I said, your homework is to read this journal paper, and sure, it will provide you with more insights. And now we have the last chapter of this course. And today is our last lecture, because meanwhile, you have chosen your seminar presentations that you're preparing in the coming weeks. And in a couple of weeks, we will have the seminar presentations. However, there's also one update. We will have 2 or 3 more guest lectures. The first guest lecture will probably be in 2 weeks on campus. Another one will be online, and maybe a third one will be on campus. But I'll send you an update once this is finalized by towards the end of the week. Just next week, we're not meeting. You're supposed to read the journal paper or prepare your seminar presentation. And then in 2 weeks, we'll be here for a guest lecture, and I expect everyone to be present. I don't think we'll be able to stream it or record it, because there are also certain confidential things in those presentations from industry. But there will be at least 2, maybe 3 really good guest lectures. One will be online, the one in 4 weeks, but I'll send you an update about this. So I'll see you in 2 weeks again. Now, in this course, we have seen that we wanted to build big data architectures. In order to do this, we needed parallelism, just not to be processing everything sequentially, but in parallel. Once we had built these big data architectures, we saw various issues that can actually appear in big data. Like, those things can also appear in small data, obviously, like biases, data quality issues. We've seen this. And then we've seen, well, once we train our models, just looking at the accuracy or the squared error is maybe also not the right thing to do. We need to do more. So we've looked into uncertainty in learning. There was also a section on what you need to pay attention to when you run these models in production. So ML ops. We've seen now as a hot topic the natural language processing things like transformers. And now we're coming a bit to an outlook in order to process big data, and that's quantum computing. Who of you has taken my algorithms and data structures lecture in the past? Some of you, the internal students, but we also have exchange students. And in my algorithms and data structures course, which I teach in the first year, there was also an outlook on quantum computing. And today we're having this outlook again, but it will be a bit extended. And for those who have taken the algorithms and data structure lecture, like probably most of you who have taken it, took it 2 years ago or something, there's a bit of a revision. So quantum computing is a topic that has existed since around the 80s, but now for a couple of years, we actually have initial quantum computers available. And quantum computers take advantage of quantum physics with the hope of being able to process or to solve certain computational problems substantially faster. Not just faster in terms of a certain factor, but faster in terms of a better complexity class. And I'll discuss with you today what qubits are, quantum bits, which are the fundamental units of a quantum computer. And we look at fundamental operations. In a traditional computer, you know, the fundamental operations like logic gates and or not. We'll look at the fundamental operations here in quantum computers. We'll see some architectures and some algorithms, and there we'll see how quantum computing can improve complexities. So what you need to know to understand this, but since you're at the end of the bachelor's, this is definitely doable. For today, we will need complex numbers. So complex numbers are an extension of the real numbers. We have a real component A and the imaginary number I, and multiply this with B, another real number. And with complex numbers, we can extend the space or the set of real numbers. And if you square I, it's -1, but you remember this from your introduction to maths, and you need an understanding of logic gates from Boolean gates, or and, or, and not. So with quantum computing, we want to take advantage of quantum mechanical phenomena to perform computations. What we're doing today will work totally different than all the computing things you're typically doing. And when we have machines that perform quantum computations, we talk about a quantum computer. And quantum computers, for many decades, were more like a theoretical thing, and now we're starting to have some initial machines, yet they are still quite limited in terms of the qubits, so the number of units they possess. And the belief is that once we have more qubits in the coming decades, those quantum computers would allow us to solve classical problems, or would allow us to solve certain computational problems substantially faster than classical computers. There are already some made-up experiments from the last few years that have shown that quantum computers are faster than classic ones, but those were problems purely about quantum mechanical phenomena. We'll talk today more about more general problems in computing. And what quantum computers take advantage of is quantum parallelism. We'll see this later. The field of quantum computing has become more popular in the last few decades for a number of reasons. We are now able to build initial quantum computers, and there have been, or over the years, more applications towards machine learning, as well as encryption, decryption have been found. And AI, machine learning, is a hot topic. So if quantum computers address this as well, this will contribute to the hype. Now you hear all these news about quantum computers becoming better and better, and they will soon take over the world and classical computers will disappear. I personally strongly objected, because the computers we are using today, so a combination of RISC and CISC architectures, they're extremely generic. So we can use today's computers for a lot of different problems. We can program them very easily because we can use high-level programming languages, and we can get them relatively cheap, and we have lots of units in them. And they work very well for a lot of problems. Quantum computers, I think, will address certain niches in the coming decades, but they will probably not replace traditional computers at a mass scale. They will rather address certain niche problems. And today we will see why. So if we take a look at the fundamental unit in a traditional computer, that's a bit, and the bit is either 0 or 1. So it's an exclusive OR. And a qubit is a quantum bit, and a quantum bit has its two basis states, 0 and 1. But a qubit can be in both states at the same time with a certain proportion or amplitude. So this gives us a certain parallelism, a quantum parallelism, if you can be in two states at the same time. And now imagine you have 10 qubits that are connected. You can be in 2 to the 10 many states at the same time. And with a traditional computer, if you have your 10 bits, you're in one joint state. So we get a massive number of parallel states, and quantum algorithms take advantage of this. For example, in an optimization problem, that I'm not just looking at one possible solution at a time, but maybe at the same time, I look at all possible solutions of an optimization problem, and I can just pick the one that is the right one. This is at least the idea. And when we say that a qubit is in two states at the same time, we talk about a superposition. Well, that's the term used in quantum mechanics. And we can represent such a qubit definition. What we use is this bracket notation. So this one here is pronounced as an A ket, but ket not like the pet, but KET. This is a notation coming from physics. And our A ket is our qubit. And it has these two components, 0 and 1. 0 and 1 are the basis states. And the 0 we call 0 ket, and the 1 is a 1 ket. And then it has a certain amplitudes to be in the one state as well as the other at the same time. So this amplitude is called alpha for 0, and typically we use a beta for the 1 ket. And you can describe our A ket simply as a vector of these two amplitudes, 0 and alpha. So our 0 ket, because eventually we see this vector as a linear combination of our basis states, our 0 ket is just a vector that is 1, 0, and the 1 ket is 0, 1, which represents the other base state. So, and then if we multiply an alpha with 1, 0, we have a 1, and our beta is the second component. So these are these complex amplitudes, or they are probability amplitudes, but now it's important that alpha and beta are complex numbers. So they're not real numbers. And in order for A ket to be a valid qubit, we need to satisfy a certain constraint. And if you take the absolute value of alpha squared plus the absolute value of beta squared, remember these are complex numbers which have its two components, and if you add up these two squares, it must be 1, and then you have a valid qubit. This purely comes from quantum mechanics, and we adopt this in quantum computing. So it's a very different representation of the most fundamental unit. And now, in traditional computing, we have our fundamental operations, not and or. And so we need fundamental operations in quantum computing. And what we use are this time quantum logic gates, or simply quantum gates, and they represent a fundamental operation on a small number of qubits. And those are the building blocks of bigger systems, because when you start in your first semester with an introduction to computer engineering, what you learn is how to put these logic blocks together in order to build more complex functions. And nowadays we use high-level programming languages, so we don't need to wire logic units together anymore. Unless you use maybe a more low-level programming language that is maybe closer to the machine, like assembly, for example. And in quantum computing, we also have these fundamental units, and we plug them together. And here already comes one big limitation. The reason why we can build very large computer systems nowadays is because we have high-level programming languages. We can abstract a lot of these lower-level issues by simply thinking in a higher order. With quantum computing, we are not really there yet. Most of today's quantum computing still addresses these very low-level units. So you also need an understanding of quantum mechanics, plus you need to come up with the right gates combined in order to compute the function that you want. And this is far more complex than just with Boolean gates. And I think this is one of many reasons why today's quantum computing is limited, because it's very difficult to come up with a new algorithm that does something useful, because you're just at this very, very low level, or you're at these very low level operations you're dealing with. And what would be cool is more like a high level programming language that you're describing in high level what you want, and this maybe gets mapped to some fundamental layers. But this is not there yet at a working scale. And this is probably one of the many things that are limiting quantum computers today. But I'm discussing this in this big data course because many of you are close to finishing your bachelor's program, and then you'll be working in industry at some point. And I'm sure in the coming years and decades, there will be more and more quantum computing applications. How and when, that's something that is hard to say, but it's quite clear there will be more progress. And this lecture today is meant to prepare you for this, so you have the tools at hand to observe what is changing in the coming decades. Now, the most fundamental quantum gate is just a NOT gate. So we also have a NOT gate in Boolean logic, and we just flip from 0 to 1 or from 1 to 0. And such a NOT gate is also often called in quantum computing an X gate. And the X gate just flips the amplitudes. If you remember from just here, we have an amplitude alpha for the 0 ket and a beta for the 1 ket. And if you applied a NOT gate to this, you can just flip them. And the way you would often write this is we have a function X, our NOT gate. It's the equivalent of the classical NOT gate. And we put in our qubit, which is alpha times 0 ket plus beta times 1 ket. And the result of this, applying the NOT gate, will be just beta times 0 ket plus alpha times 1 ket. And the beauty of quantum computing is that we can express all of these operations in terms of complex linear algebra. And our X operation can be represented simply as this logic gate or as this gate. Because what we can say is from before, remember with our definition of a qubit, which was alpha and beta, and their absolute value squared need to add up to 1. Remember, alpha and beta are complex. And we can have a sample qubit now. We have these complex numbers, 0.6 and 0.8, but here they just have a real component. And if I square 0.6, it's 0.36. If I square 0.8, it's 0.64. And I add them up. So we see this is actually a valid qubit. In practice, it'll be more complex because we add an imaginary part. And this is our qubit. And we multiply the qubit vector from the right to this matrix. And we see the 0.6 will finally be just at the bottom and the 0.8 at the top, because this is our matrix X. And you just multiply the vector from the right. So we see for the first row, we keep the second component, which is 0.8. And for the second row, we keep the first component. So this is the most fundamental quantum gate you could be thinking about, just flipping these amplitudes. And it turns out there are more complex gates. One is actually a gate that allows us to create a superposition. So we have this superposition here, but how do we actually create a superposition? When you have your quantum computer, it's a quantum system and you somehow need to try to isolate it from the outside environment. But somehow you need to be able to access it from outside and put in some information when you're starting your computation. It will be some classic input from outside. And that classic input is classic, so it's not in a superposition. And that's why we need to be able to start from these classic inputs and somehow map them into a superposition. And then we have some parallelism, and from there we can take it with more operations. What we want to do is we have a 0 ket, and we want to map this to a superposition, and we want to have a 1 ket to map this to a different superposition. And it turns out that we have such a matrix available, and this is called, or the matrix that represents this gate is the Harder-Matt matrix, or the Harder-Matt gate, named after the person who came up with it. And we have a matrix that has entries 1, 1, 1 minus 1. And each element has a factor, which is 1 divided by the square root of 2. There's a certain constraint on what these matrices need to look like. We'll be seeing this in a moment. And this 1 divided by square root of 2 simply makes sure we have this constraint. And now this is something you can try out. We have our 0 ket, which is just 1, 0, because it represents the 0. And you multiply this from the right with this matrix, you will get eventually a vector, which is a 0 ket plus 1 ket divided by the square root of 2. Very easy to try out. You just multiply the vector 1, 0 from the right. And what we have here is an equal superposition. So it's equally in 0 and 1. And we need this normalizer just to make sure that we have valid qubits. Now we're able to create a superposition. And eventually we need more gates in our quantum circuit. And this is a high-level description of a quantum circuit. For example, I put in a 0 ket, another 0 cat. So I put in 4 qubits. And eventually there are some operations in here. Which ones for now doesn't matter. We have this operation, which is actually called a C NOT. It's a conditional NOT. We have some other gates. Maybe this one could be a harder MUT gate. And once we have finished these computations, we still have our quantum system that is in some superposition. But we need to map this to our classical world eventually, because we want to get something out of the quantum computer, and that will be a classic value. So we need this operation here, the end, which is a measurement. And the measurement is a probabilistic function that returns me a classic value. For example, if we go back to our, say we have a qubit that is an equal superposition of 0 and 1. If I measure this one, what I can get back as a classic value is either a 0 or 1. And if I run this experiment many, many times, say 1,000 times, I would expect around 500 times I would get a 0 out and about 500 times a 1. But that doesn't get me anything yet, because the harder MUT gate is something I'm starting with to create a superposition. And from there, I do more computations. And eventually, I want to have maybe more clear qubits. And say I have a qubit like this one here, and I measure it many times, it will more often, quite more often, deliver me a 1 rather than a 0. But still, when I run the experiment the first time, I may get a 0 because it's a probabilistic operation to do the measurement. And that's why what you also need to bear in mind is when you run a quantum algorithm, you're not just running it once, but often many, many times. And then you would just record the distribution of what you're getting back, and then probably pick the most likely result you got out. But it's all highly probabilistic. Just different to classic computing, because in classic computing, you have a lot of deterministic algorithms. There are also probabilistic ones, obviously. But in quantum computing, it is all probabilistic. So this is the measurement. And the measurement has one more effect. If you measure a quantum system, you're destroying the quantum system. So it's an operation that you cannot reverse. Once you have measured, your quantum state is gone. You only have a classical state. You're wondering, why is this the case? This comes from quantum mechanics. And I think that's, again, a huge problem when it comes to building software that uses quantum computers, because you cannot really debug them. Because for debugging, seeing what's in, you have to measure, and then the game's over. And then you're unable to take the next operation. So I think this is something that many people are not talking about a lot recently, but I think it's a huge limitation when it comes to debugging. Now, I said a few slides ago that there is a reason why I put this factor 1 divided by the square root in front here for each element in the matrix. Quantum mechanics requires that our quantum gates are not just represented by some kind of matrix, but by a so-called unitary matrix. And what we need here is not just linear algebra, but complex linear algebra, because we are using linear algebra on complex numbers. And there is a constraint for our unitary matrices. If you have a unitary matrix U and you apply the adjoint operation to it, this cross here is often just called dagger. So you would pronounce this as U dagger. We'll see this operation in a moment, what the adjoint does. And you say U dagger times U, this must be the identity matrix. So the matrix that is all 0 except the first diagonal, which is 1. And this must be the same as U times U dagger. And if you have a matrix U that satisfies this constraint, then it's a unitary matrix, and that's a valid gate for quantum computing. Why is that the case? Or why is that necessary? This dagger operation I'll show you first what this dagger operation does is, I have a, say, a 2 times 2 matrix, A, B, C, D, and I apply the dagger to it, and I'm computing the adjoint. What I see is I'm transposing the matrix. I have A and D in the diagonal, and B and C are flipped, so it's a transpose. But I'm also putting this bar on top, and remember, A, B, C, D are complex numbers, and if I put this bar on top of it, I'm just inverting the imaginary part. So we see a sample matrix here, which is maybe not a unitary matrix. Unitary comes later. It's just an example. So we have a 2 times 2 matrix. The first entry is 6 minus 3i. Next entry is 2. Then 9i minus 2 plus 4i. We transpose it, so we are flipping the 2 and the 9i, plus we are applying the inversion of the imaginary part. So we see the 6 minus 3i becomes a 6 plus 3i. The 9i, which came there through the transpose, becomes minus 9i. The 2 just stays, and the last element turns from minus 2 plus 4i to minus 2 minus 4i. This is the adjoint operation. And what is the adjoint now used for? We see the adjoint of U times U must be the identity matrix, or just U times U dagger. And with this, we are able to do reversible computing. If all of our gates are represented by unitary matrix, I'm able to undo it. Because if I have U and I multiply it with U dagger, I'm just getting the identity matrix. So I'm able to undo an operation. And in Boolean logic, there are certain operations you can undo. For example, a NOT gate, you can just apply NOT again. So twice, or just NOT in a row, you're just undoing it. But for example, if you have an AND gate, you are unable to undo it, because with an AND gate, you put in 2 inputs and you get an output. And from that output, you're not able to infer your 2 inputs. But with quantum computing, we can do irreversible computing, and we'll later see what this is useful for. I had shown you before the Hadamard gate, and I said the Hadamard gate is a valid gate. I have its matrix down here, which is this one here, just 1 divided by the square root of 2 of 1, 1, 1 minus 1. And if I apply the dagger operation to it, and I multiply U dagger times U, this is your homework to try this out, but it's just basic linear algebra. Eventually, you will get the identity matrix. So we see the Hadamard gate is a valid gate because its matrix is unitary. Now, you're wondering, what is this useful for? Quantum computers are messy because I've said already the measurement is probabilistic. Plus, there is one more issue in quantum computers that any quantum system has that is exposed somehow to the real world. It's called decoherence. Decoherence means your quantum system will interact with its outside environment and it will lose its purity. And the longer your computations take, the more computations you have in a row, the more it will decohere. That's a problem. And decoherence is, again, a probabilistic effect that will reduce the purity of your states. So if you run the same quantum experiment twice, quantum or decoherence will affect you differently. Plus, then you still have the uncertainty of the measurement. So all about quantum computing is highly probabilistic. I've said measurements not just measure, but they also destroy your quantum system. And then your alpha and beta are gone. This is something that was all described in the 80s. And then the question was, how can we build quantum computers? Nowadays, we have multiple approaches to quantum computing. Yes? You can try to control the decoherence, and there are ways to measure it. Now you wish you have no decoherence at all. that's again a problem, because somehow from outside you need to be able to manipulate your quantum system, because you want to run certain operations. And if you were able to fully isolate it, which you're not able to do, or maybe you isolate extremely well, it would be more difficult for you to manipulate it from outside. So super little decoherence may lead to better computations, but accessing the quantum system is also a problem. And how to measure the decoherence is something we see in the course, but I'll talk about the quantum computing course later. Has anyone of you already taken the quantum computing course? Because it's an elective, so okay, you have taken it, fine. Because most students pick it in their winter semester, in the 7th semester. But this is not a 6th semester, so you're still free in picking the quantum computing elective next semester. And there are different models of computation. There are different approaches. You can have universal quantum computing, for example, certain architectures that are built by IBM. And these architectures, they have maybe 50 qubits at the most, but they also decohere. So you need to address the decoherence. And by addressing decoherence, you could use error correcting codes, for example. But then you need to use some of your qubits just to address the decoherence. So you have even less qubits left for your actual computations. That's a problem. There are other approaches like quantum annealers or adiabatic quantum computing. Those approaches even have thousands of qubits, but they are not universal, and you cannot access thousands of qubits at the same time. So there are different architectures. Now you're wondering, how can you get started with quantum computing? I offer this elective with Professor Kuhnhardt in the winter semester. All you need to do to take the elective is have an understanding of complex numbers and linear algebra and algorithms. There are some students who already take this in their 3rd semester, some in their 7th. So it's totally up to you if you pick it as an elective or not. Our elective can be a start, but there are other ways as well. For example, you could use Qiskit. Qiskit is a library for doing quantum computing on your local computer, but then it's all emulated. So you're not having real quantum effects in your local computer. Rather, you're emulating this, and you're not able to emulate this for thousands of qubits because your computer, even a huge server, will run out of space very quickly. You can do this for a limited number of qubits of simulation. But the good thing is with Qiskit, where you so it's a Python library, and you combine the operations in the right way. We'll see this later, how to do this in an algorithm. You can either simulate it, or you can just switch to a real quantum computer. And now the question is, where do you get a real quantum computer from? I have one example here from D-Wave. It's the adiabatic quantum computing approach, but they have nice photos, so I put this here. They have multiple types of quantum computers available. For example, the 2000Q from a few years ago. And this one has 2048 qubits. But it's not universal, and you're constrained in how to use them. And eventually, that chip, there's a small chip in here, in this computer, is made of niobium. And niobium becomes superconductive if you cool it down to 15 millikelvin, which is minus 273 something Celsius. Then niobium becomes superconductive, and you can have on that chip quantum mechanical effects. If you want to buy one of those machines, you have to pay about $15 million. And the machine looks huge because most of this machine is actually just a cryogenics to cool the chip. And for the cryogenics, you needed to spend at least before COVID and before the energy crisis, looking at US energy rates like 1 million per year just for the cooling. So you can imagine how expensive this will be now here in Germany. But the good thing is, you don't need to buy one upfront. You can also use them through the cloud. D-Wave Plus, this is not now marketing for D-Wave. There are other vendors as well, IBM and so forth, with other architectures. They run a few quantum computers on their own that they have built, and you can get an account and you get like 1 minute free per month or something like this to run computations, and you're just writing the code in your Jupyter notebook or something locally, you're simulating it for something, and at some point you can just switch a flag and run it on a real quantum computer for free. If you need more than 1 minute, so that's just some code example here from D-Wave, it's just a Jupyter notebook. If you need more than 1 minute, you can buy some tokens. So you don't need to spend the 15 million upfront. There was once some discussion whether we could get a quantum computer for our university here, but frankly speaking, this is not possible. So what we have seen up to here is, for quantum computers, we need a big quantum computer that is expensive. Programming is difficult because we need to put the right, and there are more fundamental operations than the harder MUT and the NOT gate. We need to put them in the right way together. It's all low level. Plus, we have all this uncertainty through decoherence, measurement, and so forth. Another question is, does all of this actually work? How many algorithms are there actually from the quantum world? And there's a very good website, it's called the Quantum Algorithm Zoo. And in this Quantum Algorithm Zoo, which is a website run by Scott Aronson, one of the gurus in quantum computing, he collects about 100 algorithms or something that others have proposed in papers. And they determine their O complexity and so forth, and why they are better than traditional algorithms. How many of them are actually useful? Probably less than a handful of algorithms. Most of them are purely addressing academic problems. We'll be looking at some of them in a moment, but we see coming up with your own quantum algorithm to address a new problem in a better complexity class, probably that's not that easy. So we need more abstraction probably in order to address this issue, plus better quantum computers that not just have 50 qubits, like an IBM machine that offers universal quantum computing, but probably tens or thousands of qubits or more. The question is, can we reach this? Right now, it's unclear. So when you talk to, I don't know, people at IBM and others, they have these fancy roadmaps and they say, yeah, in 5 years, we have thousands of qubits. But when you talk to them in private, they are far less confident about this than in their slide deck. So it's not just engineering, it's lots of fundamental research in order to build such quantum systems at that scale. Because something that is also noticed, at least with today's architectures, if you add more qubits, you're adding decoherence. And if this is just a linear effect, maybe you're doubling your number of qubits, but you're also doubling the number of qubits you need for addressing the decoherence, for example, in an error correcting code. So you're not gaining anything, you're just putting in more qubits, but practically you're unable to use them because of the decoherence. And there's a term that, for example, IBM uses, it's called the quantum volume. It's not the number of qubits, but the number of qubits you can effectively use for computations. And that's what we want to increase, the quantum volume. And how far this quantum volume can be increased in the coming years and decades, that's absolutely uncertain. And we will be seeing how this evolves. My hope is we're making progress, because then soon we can address some really fancy problems. But we'll see if this is actually happening anytime soon. Now, we'll look at a couple of quantum algorithms now. Most quantum algorithms, they have some pattern in common, some steps that you would typically take. Typically, you would start with qubits in a particular classical state, all 0, 0, 1 combined, whatever, per qubit. Classic, because you're putting those classic values in the system from outside. Then you have to somehow create a superposition from there, because we need superpositions to take advantage of quantum parallelism. You would do some operations specific to your needs. Which ones, we'll see later. And at the end, you're taking a measurement. And the actual difficult part is this one here. Which fundamental operations shall I combine in which way in order to do my computations? This is some scheme that you find among most algorithms. And I've already told you we are working in a purely non-deterministic or stochastic way because we have decoherence plus uncertainty in the measurements. Now, there are some algorithms that were described over the years. And there's one algorithm, it's called the Deutsch algorithm, named after the researcher who described it. And he said the following. We have a function where an input is 0 or 1, and the output is 0 and 1, 0 or 1. And we have all these four possible functions up here, like a 0 gets mapped to 0, a 1 gets mapped to 0, both get mapped to 1, 0 gets mapped to 0, 1 to 1, or just flipped. So these are the four possible functions. And we have now some function from the scheme, and we want to know if it's balanced or not. Balanced would mean that f of 0 is unequal to f of 1. So balanced is one way, or constant. And a constant function, we would have f of 0 is f of 1. This is purely a theoretical problem. It's made up, but when we have and it's a toy problem that Mr. Deutsch described in 1985 and showed that quantum computers, at least theoretically, provide a speed up to solve this combination or combinatorial problem. This was extended a few years later or generalized with the Deutsch-Joscha algorithm. Now you have a function that has n many inputs of zeros and ones, and it would map that input to either a 0 or 1. So we're putting in effectively a string of zeros and ones, and then we output a 0 or 1. And here we would say if a function is balanced if exactly half of the inputs go to 0 and the other half goes to 1, or it would be constant if all the inputs go to 0 or all the inputs go to 1. Now, we have 2 to the n many inputs to this function because we have a string of length n, and each character is either a 0 or 1. So we have 2 to the n many strings we can put in there. We want to determine, is this function, where n could be very large, is this function balanced or constant? In classical computing, this would take exponential time to determine because we need to go through all 2 to the n many strings. So classical computing O of 2 to the n. But it was shown that with the Deutsch-Joscha algorithm that takes advantage of quantum mechanical effects, we can get an exponential speed up to determine if some function is actually balanced or constant. This was a major breakthrough in quantum computing because it led to an exponential speed up. It's probably, again, a toy problem because we don't really care about something like this, but this has sparked lots of interest in quantum computing. And now we're coming to another algorithm. I mean, how these algorithms work, this is something that we discuss in this quantum computing elective. Some students pick, for example, the Deutsch-Joscha algorithm as a seminar presentation or something. But there are now 2 algorithms that are really helpful for real-world problems. One is the Grover's algorithm, which addresses a black box function. So we have a black box function, and we could put n many different inputs in it, and one input is a solution. And we don't know how this function works. We have n many possible inputs, and one input is exactly the right input we want, where this function returns true. For all the other inputs, it returns false. When we look at classical computing, yes, we could just be lucky with the first input by chance that this is just the one for which we get a 1 and we are done. So the best case is O of 1. But in the worst case, and that's what we care about in the complexity, it's O of n, because in the worst case, I have to try through all n many inputs, and maybe just the last one is the one I needed to find as an input. In average, it's O of n divided by 2, but this is still O of n. Such a black box search is highly generic because this could be any optimization problem where you have n many possible inputs, and one is just the one you want to find. So this could be used to tweak a machine learning system or some other optimization problem. Highly generic. But with classical computing, it takes O of n, which is obvious because it's a black box. We don't know how it works. Now, the Grover algorithm takes advantage of quantum mechanical effects and, superposition, quantum parallelism, and a couple of other things. And the Grover's algorithm solves this black box search in O of square root of n. So it's a squared speed up. Imagine n is 1 million. So with the traditional one, we have the number of fundamental operations we have is somewhere in the order of 1 million with the classical O framework and a classical computing. But in our quantum computer, it's somewhere of the order of about 1,000. Concretely, the factor is pi divided by 4 times square root of n, but this is O of n. And now if n is not just a million, but maybe a trillion, you can notice this is quite a big speed up. And it's a highly generic algorithm. I can use it for all sorts of optimization problems. The issue is it's only a squared speed up, which is already enormous, but quantum computers come with the promise that they give us exponential speed ups in some cases. And this is far from being exponential speed up, yet it's already massive. If you're curious in understanding in detail, because it takes maybe 1 or 2 hours to read how the Grover algorithm works, it's also something that students pick every year in the quantum computing elective as a seminar presentation. There's a very good website. It's called quantum.country. And that's a website that provides a number of very interactive essays. So you learn something, you directly have some quizzes in the browser, and with some exercises, and then the website learns how well you performed. And if you revisit the website, you get some problems again or not. And over time, the hope is that you're just understanding this very well by doing enough practice. And there's an interactive essay on how the quantum search works. It's beyond the scope of the big data course because this is just the Outlook chapter, but feel free to study this interactive essay in case you're curious. And now we're coming to the issue where quantum computing could affect today's encryption. Many encryption algorithms today are based on the fact that integer factorization is computationally tough. Because if you have a very large integer that is the product of 2 prime numbers, finding these 2 prime numbers is tough. You need exponential time. If you use the general number sieve, just slightly under it, making some assumptions, but let's say around exponential, it's a problem. So it's tough, and that's why cracking today's encryption is tough, and that's why people use encryption. The Shor's algorithm, so if you look at the general number sieve, the complexity is O of E of whatever here. Looks ugly, but that's the complexity. And using the Shor's algorithm, we can solve the integer factorization problem in polynomial time. Again, looks ugly, but this comes from the papers, but this is in polynomial time. So the Shor's algorithm gives us an almost exponential speed up for integer factorization. It's polynomial, so it could still be a bad polynomial, because polynomial doesn't mean it just runs quickly. If you, I don't know, look, for example, at a bubble sort, it's also polynomial, but far slower than a quicksort, for example. But polynomial is far better than exponential. And what could happen in the coming decades is if we have larger and larger quantum computers available, we could use them to crack traditional encryption because we would need far more qubits. But once we have this, this could be happening. And then today's encryption that is based on integer factorization is over. If you look at Google and other IT companies, they are spending enormous amounts on new encryption methods. There's also some standardization going on. There are some candidates. IBM is also involved in this, plus many others. And in the standardization, there are now a couple of new algorithms for encryption that could not be cracked efficiently with a quantum computer. And the standardization is processing. However, it's been noticed there was a candidate that looked safe, that a quantum computer wouldn't be able to crack it easily, but then it was found out with a classical computer, you could easily crack it. And that's why the standardization right now is a relatively lengthy process. It's been argued that the NSA tried to undermine the standardization and bring in or sneak in some algorithm that they could crack very easily, but it was detected in the standardization. And the NSA, for example, right now, whatever data they are finding, and they're clearly also saying this publicly, even if they cannot crack the encryption right now, they're just storing it, and maybe in 20 years, they can crack it once we have larger quantum computers. We'll see how all of this evolves. If you're curious about the Shor's algorithm, again, there are lots of papers on it, but it also takes a couple of hours, so it's beyond this Outlook lecture today. However, the Shor's algorithm, well, yes, major speed up, but only constrained to integer factorization. And the Grover's algorithm is highly generic, but it's only a squared speed up. We can compare quickly these four algorithms in a table. There are four properties of our algorithms we want to assess. One component is, or one property is called performance. Performance doesn't mean speed. Performance here means the algorithm solves a task well. Speed up means runs faster than classical competitors. Faster, again, in a better complexity, not just by a certain factor. Relevance means the algorithm solves a problem that is actually relevant, so not a toy problem. And availability would mean that we have the technology available today or sometime soon to actually realize this on real world problems, or at least to get it working on real problems. The Deutsch algorithm, so it was just this basic function that maps a 0, 1 to 0, 1. Probably the Deutsch algorithm solves this task well, provides a minor speed up, but some speed up absolutely irrelevant. And yes, we don't need a lot of qubits for that. The Deutsch-Yosha algorithm, it's the same. It's a toy problem, probably irrelevant. Performance and speed up is there, and availability, well, if you make n very large, probably we need a lot of qubits, but if n is small, probably doable in the foreseeable future or maybe already today. The Grover's algorithm, so this black box search, absolutely relevant, solves the problem well, provides a speed up, squared speed up, but it's unclear when a quantum computer for this would be available so that the Grover's algorithm works on massive functions with huge inputs. We don't know. That's time will show when this is available. And the same for the Shor's algorithm, solves a real problem, maybe only one problem, while the Grover algorithm is generic, but it's also unclear when we have such quantum computers available. Now, in this course, we've done a lot of big data and machine learning. And if you have large data sets, quantum computers come with the hope that we could process such large data sets much quicker. There have been other arguments in the research as well. For example, if you want to train a machine learning system, yes, maybe we could just speed up the training a lot. And there are certain papers that address that issue, that maybe you could train certain machine learning models faster using a quantum computer. So if we have a lot of data, we can speed it up. But there have also been some arguments that maybe with quantum computers, we can learn better models from less data. That thanks to quantum mechanics, we could actually find a better generalization. That's a different approach. We'll see when all of this becomes relevant in the future. Again, it depends not just on larger quantum computers with more qubits, but it also depends, I think, on more abstraction. Because if you just have 100 algorithms in this quantum zoo and most of them are not relevant, probably that's not so helpful yet. And I think we need more abstraction, and then also more people will be able to build such algorithms. There are many, many more resources that I've put here in the slides in case you want to read this. There are even books that only address quantum machine learning, so machine learning with quantum computers. There's a book in the second edition that appeared 3 years ago that discusses various research in this field. Maybe this is something that you find helpful. You're soon about to graduate, so just keep observing the topic of quantum computing and you'll see how it evolves. If you're curious, in my quantum computing elective that I teach with Horst Kuhnhardt, this is in the winter term. We teach about the first half of the term, and then there are seminars for the second half. This course is offered as an elective to everyone in our university. All you need is complex numbers, linear algebra. If you know coding and algorithms, it's helpful, but I think we're just starting with complex numbers and linear algebra. And from there, we are building the whole course. So we have business students, engineering students taking this course. And we have been offering this course now 3 times. And what we noticed, the number of students keeps doubling every year. We started in the first round with 50 students taking the elective, then 100, and last winter 200. But if we have 200 students that want to give seminar presentations, this is becoming a little difficult for us even to assess if we have groups of 3 to 4 students per seminar topic. And our projection could be that this winter about 300 to 400 students would be taking the elective. And this is also the last time that Horst Kuhnhardt will be joining our course, because he'll be retiring next year. And then it's only me left end of next year. So this year, the course will be limited to 100 students who can take the elective, because it doesn't make any sense if we suddenly have groups of 10 students that present 5 minutes or something like this. That will not be working. So if you're curious in the quantum computing course, once the courses are there in iLearn, which probably are there in August, September, I don't know when they are created, I'm not involved in this, the first 100 students that sign up are in, and then the course is closed. And probably next year, so end of next year, I need to set this to 70 to 80 students, because then it's only me teaching the course, and Horst Kuhnhardt will be enjoying his well-deserved retirement. But if you're curious, you're most welcome to sign up for the course. And we're not done with the lecture part. And I hope you enjoy your own journey preparing the seminar presentation on these machine learning design patterns. I have announced the dates when these presentations take place, probably, but I'll send an update. We will do all the presentations on a single day. Probably we don't need 2 days, because it's, I think, like 20 groups or 21 groups. So we can do this on 1 full day, but I'll send an update. And I'll also send an update once these guest lectures are finalized. One is from a company that uses large language models to summarize very complex issues on 1 page. That's why they're called one-pager, which they have done manually before. Now they're using some AI. They'll be talking about this. This will be, I think, in 2 weeks, but I'll send an update. Then we'll have a guest lecture that is purely online from Google. One of my friends, he is a site reliability engineer at Google. And I think what he wants to address is the CAP theorem when it comes to billions of users at the same time. So you remember the CAP theorem: consistency, availability, partition tolerance. Only 2 can be satisfied at a time. And when you have billions of users at the same time, there are some challenges. So he will talk about this. This should be, I think, in 4 weeks, and it's only online. And then a few weeks later, we may have another guest lecture, but I'll inform you in iLearn once this is finalized. And if you have any questions on your seminar presentation when you're preparing it, let me know. You can get in touch by email. You can come to my office hours. We can have a video call, whatever, during the term, and I'll be happy to assist you with that. Thank you very much, and enjoy the afternoon.